All right, guys, welcome to another episode of Robo Papers. Super happy to have Tong, Zhang and Boyuan Zheng dialing in to share their work called HuB, Learning Extreme Humanoid Balance. Thanks for coming on, guys.
Thank you, Michael. Thank you, Chris. I'm Tong. I'm Tong Zhang. Yeah, I'm great. It's my honor to be here to talk with you about our paper. And yeah.
Yeah, maybe
Okay.
some background on yourself, Tong, first.
Oh yeah, of course.
And then Boyuan.
My name is Tong Zhang. Currently, I'm a PhD student at Tsinghua University, advised by Professor Yang Gao. And currently, I'm also a visiting scholar at UC Berkeley, advised by Professor Kuto Swinners. My research interest lies in embodied AI, and my interest I focus topics in such as robot manipulation, humanoid robots, and whole body control.
Excellent.
Boyuan? Okay. Thanks for Michael and Chris for inviting us. I'm Boyuan Zheng. I am an incoming PhD of Professor Yang Gao, and now I am a senior undergraduate at Tongji University. And my research interest lies in humanoid whole body control. Yeah, thank you.
Perfect.
Thanks.
Yeah, so maybe if Tong, maybe if you can share your screen, if you can go through, we can just go through the overview.
Yeah. Okay, let's start. Today I'm going to present our paper, HuB, Learning Extreme Humanoid Balance. Before we dive into the presentation, let's first take a look at a real-world experiment video of our methods. Our methods allow humanoid robots to perform extreme balance poses, like the slalom balance or Bruce Lee kick, and stay stable even under strong external disturbance, like being forcefully hit by a soccer ball.
Very cool. Very impressive. How many of these poses did you do?
We did 6 poses, 6 challenging extreme balance poses, and this shows that the humanoid can successfully complete more than 10 consecutive executions in a single take without any failures or external interventions. This demonstrates HuB's strong reliability and control stability in real-world deployment.
That's really cool, man.
Yeah. Okay. Yeah. The motivation for this work comes from a contrast between humans and humanoid robots. The human body demonstrates remarkable balance capability. For example, this figure Bruce Lee standing firmly on one foot while performing a high kick over 1.5 meters, maybe. Such feats rely on finely coordinated whole body control, rapid feedback loops, and exceptional stability.
I should just say most humans can't do that. Like maybe only Bruce Lee can do that, but still,
not
a human like Bruce Lee can do that.
Yeah, actually, we have tried to do this, but we failed to do this. Yeah.
Yeah, for sure.
Yeah. In comparison, humanoid robots still frequently fall. They often lose balance when encountering external disturbance, attempting challenge poses, or operating in unstructured environments. This gap highlights a key limitation in current humanoid capability. This leads us to 2 central questions that motivate our work. The first is that can humanoids achieve extreme balance, such as performing single-leg poses like Bruce Lee's kick? The second is, how can we design control policy to enable such capability? Can we develop a learning-based controller that fully exploits the hardware's physical potential and allow robots to perform such challenging balance behaviors? In recent work on learning-based humanoid control, a common approach for enable humanoid to perform diverse motions is to train a control policy to track reference motions, such as OmniEdge tool. It's a Coral 2024 paper. The standard pipeline typically begins by obtaining human pose, either from a video-based motion capture algorithm or marker-based motion capture system. These human poses are then retargeted to humanoid-specific reference motions. Next, a control policy is trained in simulation to track these reference trajectories. In some cases, A teacher-student framework is used to improve learning efficiency. Finally, the learned policy is deployed to the real-world robot. However, we found that this pipeline faces a significant challenge when applied to complex balance tasks. The first challenge is due to reference motion error. For tracking-based methods, the successful execution of high-precision balancing critically depends on the accuracy of the reference motion. However, video-based mocap algorithm often introduce significant error. And although marker-based motion capture system offers better precision, they are impractical for internet videos or consumer-grade recordings. Moreover, optimization-based retargeting can further degrade reference quality due to non-convex optimization, imperfect model alignment, and a lack of temporal continuity constraints. These issues can lead to artifacts such as foot sliding, even during stationary phases, which cannot be tolerated in demanding balance tasks. This inaccuracy poses challenges for humanoid attempting to perform complex balancing tasks.
So I just want to be really quick. One clarifying question. So I think the idea is that basically, so you showed us a bunch of these very cool videos that only your method can do at the beginning of the presentation. So basically, these are the reasons why we couldn't use AMP or Deep Mimic or any of the other many previous methods to do this, right? Like all the dancing videos people have seen. Is that, just to be clear, is that right?
Yeah. Well, we use similar methods like Deep Mimic, but we find there are some challenges to do this. To do this challenge poses. Yeah.
All right. Sorry. Go ahead. Yeah.
The second challenge is that is in training balance policies. Even with relative accurate reference data, training balance policies still presents significant challenges. Due to morphology differences between the human body and the humanoid, their center of mass does not necessarily align. As a result, strictly tracking the reference motion does not always lead to stable balance for the humanoid. The third challenge lies in sim-to-real transfer. This gap between simulation and the real world is a fundamental challenge in robot learning, but it becomes especially problematic when we are dealing with the complex balance tasks. In the real world, sensors like IMUs and visual inertial odometry often produce noisy signals. This leads to inaccurate policy input, which in turn cause jitter actions. The instability can build up and create a vicious feedback loop that makes the robot lose balance. The second thing is that in our experiment, we observed that prior tracking-based methods frequently result in wobble or jitter during real-world balancing. These phenomena primarily arise from modeling discrepancy between simulation and reality, particularly in the simulation of ground contact and friction interactions. So, how do we solve this? Next, Boyuan will explain how HuB is designed to tackle these challenges.
Okay. So, I will introduce what our method do to enhance the robot, the humanoid's balance capability. As Tong just explained, we identify 3 critical challenges for humanoid balance learning. So with HuB, we will tackle these challenges head-on through 3 targeted solutions, as you can see here on the slide. The first one is the challenges due to reference motion errors. To tackle this, we need to enhance the quality of the reference motion data, so we design the reference motion refinement process. And the second one is for balance policy learning, we introduce a balance-aware policy learning strategy to guide the policy to learn more robust balancing behaviors. And thirdly, to bridge the sim-to-real gap, we design some components for sim-to-real robustness training to help the policy adapt to real-world noise and changes. And in the next part, I will present the three-part solution in detail. So the first one is the reference motion refinement process. To mitigate reference motion artifacts, we introduce a set of motion refinement strategies. So the first one is SMPL, is initialized retargeting. So during the retargeting stage, some existing methods like OmniH2O start by setting all join of the humanoid to a zero pose and then optimize by minimizing the differences between the key point position. But in a non-convex optimization, this can lead to poor results because the zero pose may be very far away from the optimal, the best solution. So for example, as you can see here in this figure, in a squatting motion, initializing from the zero pose can result in a posture that is quite different from the original one, the SMPL body, and deviates significantly from the original motion. So we want to improve this. So we introduce a better initialization strategy, which is very straightforward. It's based on the SMPL human pose. You know that the Unitary G1 robot has 29 degrees of freedom. So since the humanoid joints are a subset of the SMPLs, we can initialize each joint of the humanoid using the corresponding SMPL Euler angles. So this gives us a much better starting point, which is much closer to the optimal pose and can speed up convergence and improve accuracy.
Boyuan, can you share a little bit more, like what exactly is SMPL? What does it stand for?
Oh, okay,
SMPL.
SMPL.
Yeah, Boyuan.
Okay, SMPL is a format of like human body motion. It's like it has two main parameters. One is for human pose, the motion human motion, and another one is for like morphology. So SMPL format can store human motion data. Yeah, it's a format. So
Got it. And,
yeah. I mean, like AMS. You know, AMS dataset is a very huge humanoid motion dataset. It is stored by the SMPL format. Yes. Okay.
So just so can you just to go on that a little bit more? So what would be the before this? What would be the other way of doing this? Like what do you compare? What would you compare to?
Like in Human Plus, they just simple copying the SMPL angles to the humanoid, and because that there's a lot of morphological differences, so the n-factor positions will be much different. But in like Omni H2O, they use a zero pose, like, and so they initialize the humanoid joint with a zero pose and then do a optimization by minimizing the differences between the SMPL joint position to get optimized optimized humanoid joint. But a zero pose may be very far away from the optimal pose.
Okay.
So
yeah. Okay, so previous work you started with a zero pose, so like just like a T pose essentially, or some like a normal pose, right?
Yeah.
And then you optimize until you get to the until I guess to satisfy all the constraints, we're getting as close as possible to the joints. And here what you're saying is instead of doing that, you find the closest possible SMPL Euler angle and then use that as the initial guess. Okay.
Yeah.
That makes sense. Yeah.
Okay.
All right. Thanks.
Okay, and the second one is the grounded food correction. So during retargeting, after retargeting, there are a lot of food sliding in the reference motion caused by mocap noise or the retargeting errors. So to further enhance our retargeted motion quality, we've added a data post-processing step to fix the food instability caused by such errors. So here's the key idea. When a food is grounded in the original motion, we assume that it shouldn't slide and should remain stationary. So during single food support phases, we keep all of the joint angle of the humanoid unchanged and adjust the global root position to keep the grounded food perfectly still and its precision is unchanged across frames. And this adjustment can eliminate unrealistic foot sliding from noisy poses or retargeting imperfections, and is way more easy for the policy to learn.
Does feed into
okay.
the optimization problem at all? Like, because that's presumably an extra constraint, or no? Do you solve those separately?
Can you say it again?
Does this go into the optimization problem in the first part at all, or is those just separate steps?
It's
Yeah, separate step. It's
it's
a post-processing step. Yeah, after the retargeting. Yeah. Okay. So the third one, humanoids may look a lot similar to humans, but actually their mass distribution is actually quite different. And on top of that, the motion capture algorithm we use comes with its own errors, and these two factors combined often lead to significant center of mass shift in the reference motion. And this is particularly noticeable during the single leg stances, where balance is the most critical. So therefore, we think that implementing COM, which means center of mass based filtering, is essential for selecting physically plausible motions. So what we do is that we calculate the COM using the body masses and positions defined in the URDF of the Unitary G1 robot, and then filter out any motions where the projected center of mass on the ground shifts more than 0.2 meters from the support through the center. And this can ensure that we only keep relatively physically feasible trajectories. Okay, and the last one is the transition stabilization. Because balance critical motions are very sensitive to initial conditions, to the initial pose. So even minor instability during the preparatory double support phase can significantly compromise the performance of the balance motion. So to address this challenge, we propose to extend the double support phase, both preceding and following the target balance motion. In detail, our approach duplicates the initial and the final frames to make the double support phase match the duration of the balance phase. And the benefits are that first, during policy training, it increases exposure to stable stances, which can facilitate more robust balance training. And secondly, in real-world deployment, it provides a necessary settling time for the policy to get smoother transitions into challenging pose. So to summarize, we achieved robust motion retargeting and more accurate reference motion through initialization and physics filtering and stability enhancement. Yeah.
Yeah, Boyuan, I have a question. So I suppose some of these assumptions, like for example, grounded foot correction, center of mass filtering, will probably apply for balancing acts where the robot is or the human is relatively, say, in a stationary place. Versus, I'm just trying to think, like for example, one of those, like Olympic skate dancing. They are balancing. They are always off center. The center of gravity is probably more than 0.2 meter from the foot, and they're always accelerating. Maybe would you say for those kind of balancing, that will be out of scope for this study? Or would you think it apply?
It's kind of limitation of our work. We focus more on like quasi-static motion, quasi-static balance motion. Yeah.
Got it. Cool.
Okay. So let's continue. So even with refined reference motion, humanoids face some inherent challenges in maintaining balance because there are some morphological mismatch between the data and the humanoid, and because of the lack of structured guidance for balanced behavior. So we want to overcome these issues through two paths: relaxed reference tracking and balance shaping reward. So as Tong has just mentioned, the structural differences between humans and humanoids often cause center of mass misalignment, making direct motion tracking unstable. As you can see here, even if the humanoid all of the key point is tracking very precisely, it's not a very stable behavior. So our solution is that we want to exploit RL's exploratory nature by permitting small COM adjustments in the policy. So we set a relaxed tracking tolerance in rewards to allow deviation from reference motions when needed. for balance. As you can see here, actually the foot is not tracking very precisely with the reference motion, but the whole motion is more stable. Yeah, so this can enable more stable behavior for extreme balance tasks while preserving motion intent.
So, Boyan, so does that mean, given this relaxed reference tracking, does this then therefore imply that, because you mentioned, or Tong mentioned earlier that there are two kinds of retargeting or the source data, right? Either video or those marker based, presumably using like very, very high definition video. So, but with something like relaxed reference tracking, does it mean that you can just use the video based one since you don't need super precise things anyway? Is that the implication?
Yeah. Actually, we our data is from the video mocap algorithm, because the extreme balance data is lagged from like a mass data set. So we need to select some video clips from the internet and use the mocap algorithm to get the motion. Yeah. Okay.
Cool.
Okay. So, well, relaxing tracking constraints provides necessary flexibility for balance adjustments, but this alone cannot guarantee physically plausible behaviors. Actually, unstructured RL may converge to suboptimal solution. So to address these, we need to design a comprehensive set of shaping rewards. So the first one is the center of mass reward. So in each frame, we compute the projected center of mass on the ground, as you can see the dark blue plot here. So so these reward encourage the projected COM within the support polygon of the foot, and which can ensure fundamental balance stability. Because as you can see here, if the COM is far away from this foot, it's not very stable. And the second one is the foot contact mismatch penalty, which enforces alignment between the humanoids and the reference motion's contact states. Actually, we formulate foot ground contact states as discrete contact patterns. As you can see, this blue one is the reference state. It should the right leg should stay in the air, and the low one is the real state of the humanoid. So, for instance, during the single leg balancing phases, we will penalize a pattern like this because there's some ground contact by the non-supporting foot. Yeah, so this may disobey the requirement for our task because it's the single leg balance. Yeah, and the third one is a closed feet penalty, which can avoid lower body instability by maintaining proper foot spacing. So together, these carefully designed rewards can guide the policy toward both stable and task-compliant motions. Okay, so this is the second part, balance-aware policy learning. And the third part is the sim-to-real robustness training. So sim-to-real is really a top start, the transfer and to deploy the student policy in the real world, we will encounter many difficulties. For example, there are much sensor noise from the IMU or from the visual inertial odometry, the VIO, and there are some reality gaps in dynamics. So these noise and dynamics pose major sim-to-real challenges for balance control. And in real-world experiments, we find that the VIO noise is very large and hard to meditate. So we decide to address VIO noise by completely excluding odometry data during both training and deployment. So to do so, we need to align the reference route with the humanoid current pose, expressing all the tracking targets in the local coordinate frame because we don't have any global information since we exclude the odometry data. And methods like XBody2 that only discard odometry at deployment while still using global coordinates during student training may lead to some common failure modes like uncontrolled falling or directional jumping. So in contrast, our local frame approach during both training and deployment can inherently prevent such perception mismatches. And the second one is the IMU-centric perturbation. So previous methods, they enhance the robustness of the policy through injecting independently uniform observation noise. But we think that it oversimplifies real IMU noise characteristics. So crucially, since IMU-derived route orientation defines the local coordinate frame of the humanoid, so some key observation, such as the projected gravity, the angular velocity, and the localized reference targets become inherently coupled because they are all expressed in the local frame state. So they need the IMU route orientation to do the transformation. So, simply adding independent noise will ignore this dependency. So our solution is that first we employ OU noise to perturb the route orientation in Euler angles, and all the downstream observations, such as the projected gravity, the local reference targets, are computed from it. So the key advantages are the OU noise instead of the uniform noise or Gaussian noise can capture the temporal correlation in real IMU noise, and because all of the downstream observation are computed from the perturbed route orientation, it can preserve the structural dependencies between the observation. So it can better approximate real sensor behavior for robust policy. And the third one is a high frequency push. Actually, in reality, tracking policies in our reality experiment, we find that they frequently fail because minor perturbation. Maybe at first it's a very minor jitter, but if the policy cannot handle it correctly, it will get progressively amplified through our model dynamic effects. So what we do is that during teacher policy training, we inject small and high frequency velocity offsets to the humanoid robot's route. So it's like we apply pushes every 1 second at the root and up to 0.5 meter per second. And this can simulate real-world instability patterns. And compared to prior work, they also use some push, but their push are like low frequency and high magnitude. Actually, they want to add this kind of push to train the policy to recover from a sudden force or a sudden strike, and it's not very suitable for our task because the extreme balance task. For extreme balance tasks, the feasible region is very narrow. So if you give a very high magnitude push, the control positive may very likely to lose control. So our high frequency micro perturbation can match the narrow feasible region of single lag balance. Okay.
It's really interesting that you're doing the high frequency push makes such a big difference. But is 1 second really that high frequency, or do you mean that like it's pushing continuously for 1 second, or like every second, or is it just like instantaneous pushes every 1 second? How is this?
Yeah, it's like every 1 second, like the interval is 1 second. Okay. We say it's high frequency because compared to a prior, they give a push like every 5 seconds. So
makes sense.
So it's relatively high frequency.
Makes sense. Cool.
So it's like 1 hertz every 1 second. You give it a push, basically.
Yeah.
Yeah, I do want to ask, right? So I know this is in simulation, but the IMU is it always assumed to be at the center of mass? Is that where you assume
what do you mean?
the IMU? So you mentioned IMU centric perturbation, right? So is it common to just assume the IMU is just placed at, like basically at the center of mass of the humanoid?
No.
I guess
Actually,
it's placed on the root, on the
it's in the pelvis of the humanoid.
Oh, I see. Is that also like the actual G1? Is that also where the IMU is?
Yeah,
Okay,
it's it varies from a different humanoid. In Unity H1 is in the torso, and for G1 is in the pelvis. Yeah.
I see. So you okay, got it. Okay.
Okay. So that's all for our method, and I'll show some real world experiment. So as you can see, we implement our method on 6 extreme balance tasks like Bruce Lee's kick and swallow balance, and we apply some external disturbances by striking the humanoid with a forcefully kicked soccer ball, as you can see here. So you can see our method can rapidly react and recovers with minimal motion, and this demonstrates a strong disturbance tolerance. So yeah.
Yeah, I'm curious. So all these originally is coming from that data set from mass, right? Is that a mass? So
AMS.
am I right?
No.
Yeah, am I right?
So these motions are not from the AMS. It's from the video clip we select from the internet, and we use the video-based mocap algorithm to get the reference motion.
Oh, I see. Got it. I see. So you guys literally found some Bruce Lee kick, and then just try to imitate that. Okay.
Yeah.
Okay, so
is it
that's all.
just one video clip? One video clip is like, for example, the Bruce Lee.
Yeah,
how many Bruce Lee
kick?
Yeah.
So what's Sasha? Could you do
one?
this for 100 different videos? Sorry.
Yeah,
Just every Bruce Lee kick is a bit different, right? I suppose.
Yeah, we trained on several video clips, and we roll out on just one clip.
Yeah.
How many video clips did you train on for each of these? Sorry. Go ahead.
About 10 in training.
Okay.
Yeah, to make it more to make it can generalize to different poses. Yeah.
Interesting. So what you're saying is that is a whole pipeline is something like just about 10 video clips of a similar action. Because I mean, Bruce Lee kick, every Bruce Lee kick is probably slightly different from each Bruce Lee kick, but let's say you get 10 similar ones, and then you throw into your pipeline, and then you do the retargeting, and then you do the second step where you have all these I guess special reward functions like reward tweaks, right?
Yeah.
Yeah.
Interesting. Do you guys do some ablation study? If you take away, because there's a lot of very carefully designed parts. I wonder, if you guys can share a little bit.
Yeah, we have to do some ablation in the paper. Maybe Boyuan can share your
in the paper.
Screen, share the
Oh,
paper, I guess.
okay, maybe. Wait.
Hey, if you could bring it up and share it, that'd be great.
Can you see it?
Yep.
Yeah. Actually, we did some ablation in simulation. Yeah, because it's not easy to ablate it in the real world. Yeah, and we did we have several metrics. The first is in the row. The first row is completion. It measures whether the policy can make the robot to complete the tasks. The second matrix is stability. It measures whether the robot can stably finish the stably complete these motions. The last one is tracking error. It shows how far the actual the real motion is from the reference motion. Yeah. The ablation shows that the first ablation is on relaxed tracking. It shows that if we have a smaller tracking sigma, here sigma means the
tolerance.
The tolerance. The tolerance of the tracking. If we have a smaller tracking sigma, we will have a lower tracking error, but the stability will be worsened. So in real world, we find that it will jitter or wobbling, and it cannot successfully finish the task. The second ablation is on balance shifting reward. We find that firstly, without COM reward, center of mass reward, the stability and the tracking error and the computation will both will all be worsened. Yeah. And the second ablation is without contact penalty. We found that without contact penalty, the completion, the success rate, will be largely worsened. Yeah. The last.
Sorry, remind me what the contact penalty was. Like this is the one for the feet being flat. No,
the other
the contact penalty is like the foot ground contact pattern is like disobey the reference motion one. They don't match. The mismatch between the reference and the real robot's feet ground contact pattern.
Got it.
But this is for the non-support leg, right? Was it?
Yeah.
Is it the one for?
Yeah.
Okay.
Yeah, for the non-support leg, yeah.
I see.
So
you're saying that it matters a lot more, actually. Oh, interesting.
Yeah, actually, that leads to. Sorry, how do you define success here? Is this the robot falling over, or is it just like human judged success, or is it like within some error tolerance? Because it's a simulation metric, so it's not human judged. Yeah.
Yeah, we have like three circumstances. Okay. Like the first one is the robot is falling, and the second one is the foot contact mismatch, which means the non-supporting leg contact the ground. And the third one is an average tracking error existing 0.5 meters.
Gotcha. That makes sense. Well, okay. So if the foot contact pattern is a part of the success metric, maybe that's less exciting than if the contact penalty drops it. That's kind of unsurprising, I guess, but reasonable. It makes sense. Yeah. Still good to know.
Because we are doing single leg poses. If your unsupport leg contact the feet, I think you did not finish this single leg.
Yeah. And actually, like in real world deployment, if you try to try to be stable by using the non-supporting leg, is very dangerous because it will be a rapid motion. Yeah.
Yeah, and the third part we did ablation on sim-to-real robust training. Yeah, this table shows that if without localized tracking, without IMU noise, without push or push in another way, such as low frequency, these all worsen their performance. Yeah.
Sorry, you said these were all simulation experiments, though. So this is sim to sim, then? Is that the?
It's not sim to. It's all both train and evaluate on ISAC team. Yeah, it's not sim to sim. Yeah.
But then why does the IMU noise matter in the sim? I guess it's still a different IMU.
We add some noise to the IMU when we evaluate the policy. Because we
gotcha.
found,
yes. All right, that makes sense. All right, cool. Thanks.
Yeah, maybe we can also see some comparison with our baseline. We did some comparison with the baseline OmniH2 in the real world. Boyuan, can you show our website?
The video, right?
Yeah. The comparison with the baseline. Or maybe I can show. Maybe I can show.
Okay.
Yeah, we did some comparative results in the real world with our baseline OmniH2. It's a tracking based, just like deep mimic, but it's did in the real robots. Yeah, and for example, if we evaluated on the task swallow balance, we found that it will fall. Yeah, it will lose balance. Yes. Yeah.
It looks nervous. It looks like it knows it's about to fall.
Yeah. As for the Bruce Lee kick, we found it's jitter and wobbling. Yeah. As for this Naja pose. And we found that this is also why we use foot contact reward. We found that
Mm-hmm.
in some cases it will not read its on-spot leg and second leg stand. Again, fails to it's completely to fail to read his on-spot leg. The last is squat, and we find it's a jitter and it's not very stable. Yeah.
Interesting.
Yeah.
Is there anything that was surprising when you guys actually test things out in the actual robot versus when you guys were doing all this simulation?
Yeah. Actually, we can do these challenge poses very quickly in simulation. Actually, it's not very we take 2 weeks to maybe 2 or 3 weeks to do it in simulation. It's not a long time. Where we did some data refinement and we did some we designed some reward so that we find we can successfully complete the challenging balance poses in simulation. But when it's deployed to real world, we find it's totally not work, and we find there are large sim to real gap. And we find I think maybe the important thing is that the challenges balance poses require more accurate parameters. I mean, it's sensitive to the noise and sensitive to the jitter. So the more time we spend in the how to transfer from sim to real, and actually we find one important thing is that random push. We find that if we simulate the jitter in the real world into the simulation, I mean we do random push to simulate the jittery in the real world. In this way, we found that the policy the policy training in simulation can perform stably and can perform these challenging tasks.
And I guess did you guys only have one G1 or you have a few G1s? I guess my question is like, do you see any differences between like individual? Because even if it's the same model, I assume like every G1 have a slightly different motor, or maybe over time the actuators wear off. Like what if they start overheat? Like does it still work?
Actually, we have just one G1, but it's a very
do you notice if it performs like worse at the end of the day after a bunch of experiments, or better, or something like that?
Sometimes you need to, after a lot of experiments, maybe the temperature is a bit high, so you need to let it have a rest to cool down. And also we broke it like for 3 or 4 times. It's really tough
in the real world.
I think I think you are right. There might be slightly difference between different G1s, and I think maybe a good way is to do domain randomization. Actually, random push is a kind of domain randomization, and we did it. We think it's a good it's deployed to different G1.
Yeah, I think this is I mean, just from the video, I think I thought it was super cool. I don't think I've seen something so extreme, like, I mean, done a humanoid, like balancing. So really, really cool.
Thank you.
Really impressive videos.
Yeah, really, really impressive, I thought. So I guess you guys mentioned 1 or 2 limitations just now. Like, for example, this is more like relatively static pose. Like, do you guys have some idea in your next follow-up paper, let's say, any new directions that you guys are thinking about to improve this further?
Actually, in graphics area, there are some tries by, I guess, Jason Peng. They have did some general purpose robot, humanoid robot. Yeah, and but actually we find but deploying them into a real world, there are some challenges. Maybe I think we can refer to this work and design how to bridge the sim-to-real gap. I think it's the most challenging thing in humanoid. Yeah, that's my opinion. Yeah.
Boyuan, how about you?
Yeah, I think sim-to-real is the most tough process. And for future works, actually, we are doing some like whole body local manipulation task for the new project.
Whole body.
Cool.
Okay, that's cool.
Mm,
Yeah.
yeah.
Obviously, you want decent balancing. You cannot balance.
Actually, we want to do some humanoid manipulation, not just fancy
Mm,
motions.
yeah.
Because we think. Well, I think this paper is to show that current humanoid hardware can do such balancing and I believe this method will help the robot to keep balance and more stably. But in the future, I think the most important thing is to enable the robots to do some manipulation, to do some work, to
Yeah, I want to say like in at least for humans, like 99.9% of the time, like you don't even think about balancing. But the one moment you nearly trip over something, you need that 0.1 second of supreme extreme balancing skill so that you don't spill the milk or something like that, right? So I think balancing is still extremely useful in those edge cases in the real world. So without that you don't know where.
Yeah, I think it's a fundamental skills for the robot, and based on this, we want to do some more manipulating tasks to do more intelligence, to enable the robot to have more intelligence. Yeah,
that's awesome. Yeah, really cool. Yeah, maybe just to wrap things up, we always ask this question: is there any recent paper that you guys I guess doesn't have to be recent, but any papers that you guys have come across that kind of really inspire you or like really blew your mind? If you want to give a shout out.
Actually, for me, I think it's not a paper, but I have seen the Tesla's recent post on the Optimus and they enable the Optimus to learn from human video. I think it's because personally we find that teleoperate humanoid is extremely hard and extremely labor. It requires much labor. I think learning from and another thing is that the reason why we use humanoid is that we can use human motion, human videos. There are smaller gaps between human and humanoid. So I think it's a good way to develop the humanoid robots. So just like Tesla, they use human videos. But of course, I think maybe there can be some hierarchical ways. Maybe we have plenty of human videos, but we also may have some small part of teleoperated humanoid with data. Yeah, I think it's a approximating way to the humanoids. Yeah, they did not. They did not publish a paper, but I think it's a good way to do this. Yeah.
Well, it's kind of aligned with what you guys have done in this paper anyway. I mean, it's also just starting from video, pretty much. Boyuan?
I think like the HuMi, HuMi from Shanghai AI Laboratory is quite impressive. They use an exoskeleton to teleoperate the humanoid Unitary G1 to do some local manipulation. Local manipulation is pretty interesting and also very useful. Yeah, so there's also some a lot of local manipulation papers recently, like twist
whole body.
Whole body. Yeah, I think it's it's like wood. It's a very valuable.
Definitely. Funny you mentioned twist. We just interviewed Yan Jie last week. His pipeline involved like mocap, all the fancy sensors. But I think he also mentioned that video is probably the way to go. I think as we scale this data collection. But it's interesting that like Boyuan, you still mentioned like HuMi, which is really teleop exoskeleton. So maybe we still need a bit of teleop, like what Tong said. Yeah. Chris, any final questions or whatnot?
I think that's great. It's been a really interesting talk. Lots of great results too. Cool stuff. Thanks, guys.
Thank you.
Thanks for inviting us.
Well, thanks for. All right, Chris, what have you learned?
Well, I thought that was a really cool. I think those are some of the coolest videos of humanoids that I've seen, as far as all the balancing. Like, it's very tough stuff to do. I thought there's a lot of like lessons in how better to set these things up so that you can build so that you can teach robots to do these kinds of hard tasks. Part of it was for me is just like learning that they can do it, and like they go through a lot of. I really liked all the discussion of all the places where where it's hard to do this normally, because I think like there's this intuition that you only see these videos when they're there's always like a positive bias, right? Like you see the things that work. So it's always nice to see someone say like, well, these are the cases where it didn't work and then we made them work, right? So I thought it was interesting. What about you?
Yeah, I think what is interesting is that they actually have a lot of handcrafted, almost like heuristics, in order to make it work, right? And a lot of these heuristics come from the fact that we humans understand physics very well, right? So, for example, like the fact that I think they have one of this penalty where if the two legs are too close together, they penalize you. But that is because we know when your legs are too close together, you tend to fall, right? You know. Yeah. But this is because we understand physics, right? Obviously, we are humans. We understand how the human body works. So multiple of their rewards mechanism is actually just based on those kind of understanding. And then it's almost like a feature that they pick out. Okay, this is important, and let's reward based on that. And clearly the ablation show that those are actually I guess like quite important, and it seems to me it's multiple of these things. So it's not in the very classic case of let's dump a bunch of data and then simulate the hell out of everything, and then so the model magically learn by itself kind of thing. It was a lot of very, very careful like tuning. Yeah, so yeah, I find it quite interesting.
Yeah, I always think there's a lot of things like that where it's very there's a lot of heuristics engineered to make the system work well. Like I do think that's to some extent that is a weakness, although it's a very common one, right? So it's not like I hold it against this paper, right? It's a very common weakness. There's the open question of like how often is this going to, how easy is it to get this to work on some new task? And I think like to your point, like the legs being too close together, like that's the kind of thing where it's very engineered and probably isn't that general, right? There's some like the foot contact pattern that I think is probably pretty broadly useful, right? Like because I think like that is like an important part of a lot of tasks. That's a part of like running and walking gates often to some extent anyway, right? So anyway, yeah, it's an fine line to walk, I guess, with all these different functions. It would be nice if there was some elegant solution that didn't require quite as much engineering, but obviously, so maybe they'll get there. I think as they do this local manipulation stuff they mentioned. Yeah.
Yeah, and I suppose some of the assumptions made were based on the fact that they were dealing with tasks that are like I guess quasi-static like balancing.
Right.
So like I mentioned just now, like let's say a skateboarder, right? It's constantly kind of on the move, or like someone skating. The center of gravity is constantly off balance in a way. So if you go with those things, then actually some of the assumptions I don't think will work, right? So for example, they remove.
Sorry, go ahead.
Yeah, they filter out some of this center of mass where the center of mass was too far away from, I guess, the contact point. But if you're skating, then by natural fact, you are actually always want to be slightly off balance so that you move forward. That's the idea.
Well, but also for like local manipulation, like let's say if I want to open a fridge door or something, I'm generally leaning my center of mass and using that as part of the action mechanism to open the door.
Oh, yeah, that's right.
So like this is why I feel like
you're probably leaning towards the fridge a little bit. You're intentionally off balance.
As a human, you don't like keep your legs planted and your hips directly over your feet when you're opening a fridge door. You actually like pull back and use your whole body, and that's true for a lot of that and most doors and most objects. Like generally, we as humans use our whole bodies to do manipulation in a way. So like this is why I feel like a lot of these heuristics just aren't going to make sense when they move on to local manipulation, but they are moving on to that. So I think they'll figure it out. I don't know.
Got it. Yeah.
I don't know.
Yeah, that's true. Yeah, but it's I would say for the domain that they selected, it's very impressive. Like the videos, definitely. Like they threw the ball and they did it continuously, right? So
I love the Bruce Lee kicking one where it like hops its ground foot a little bit to adjust. That's like really impressive and requires really fast motions. I also thought the observation that like bringing your foot down to catch yourself was actually extremely dangerous because it was a really fast motion, like with a really large like that's something that I hadn't really thought about much before. That's an interesting point that you brought up.
Which one is that? What was it?
This is when we were talking about the ablations. Boyuan was mentioning that like one thing it's actually quite dangerous to like have the robot try to bring its foot down to catch itself, right? Like which is something that I hadn't really thought much about in the past, but like that makes sense because you got to move very quickly to do that, and so it's important anyway.
It's unfortunate also. I guess I mean, they only have one unit. I always wonder, like, also, even just generalizing across the exact same so-called robotic embodiment, it's just different unit. Even it's the exact same, let's say, Unity G1 model, but every G1 is different. It's just every human body is slightly different. And all the difference is, it makes all the difference in the world. It's the difference between me and Lionel Messi, let's say, right? I mean, he's got a human body, I got a human body, I can't, So, yeah.
I don't know. Yeah.
Yeah.
Do you think so? They never do any training on robot, right? So, like, how much difference do you think it makes? Right? Because
it's very hard, I imagine, to do balancing training on the physical robot, though.
Right? Yeah. Well, you could do it with like a tethered, like a catch, right? Like you could.
Oh yeah, I guess so.
But,
Yeah,
like,
that's so.
But they don't. Like, I mean, it would take so long, right, compared to simulation. Like, I guess my point is that
that's
like
true.
they picked some set of parameters for the simulation and they ran it and they got a policy and they deployed it. So like the place where knowledge comes from robot to real is when they enter parameters into the simulation, right? So like there is a chance at least that it should just work on all the robots, right? I would kind of expect it to, unless there's a fairly noticeable difference between the robots or they did tons of tuning. Like if they really did that loop a lot, right? Does that make sense? That's, or at least maybe, I don't know.
Yeah.
Like that's my impression.
Yeah.
Right. Yeah.
Yeah.
Of course, who knows how often like things take a lot of tuning, so who knows, right? But it definitely happens with the robots. Yeah, more than you would expect, I think, right?
Yeah, I think I don't know whether this is a broader point. Obviously, I'm not a researcher, but you probably know this way better than me. I think that sometimes there's a trade-off between writing, like, how should I put it? Like, I mean, ultimately, you need to push out a paper, right? As a researcher, there needs to be some timeline. You need to time box the whole thing. And so, given some certain time limit, do you spend more time on engineering? In which case, you probably can get, a more compelling demo, right? Which obviously still draw attention to the paper. Versus say you don't care, you less time on engineering, more time on, I don't know, maybe more generalizable, say, algorithm breakthrough or whatnot. But then because of lack of engineering, the demo doesn't look that great. The success rate doesn't look that great. But maybe fundamentally there's something different going on. Yeah, it's hard to strike a balance.
Yeah, definitely.
Anyway.
I don't know. I feel like
you know this.
It's
a lot.
like it's not even just engineering, because I feel like a lot of these things come down to engineering, right? Like designing the reward functions and then models and so on is all engineering too. But like it's like what's the right engineering to do, and like whether it's the really short term polishing for a demo, or because like we were talking about Twist, right? Like that like a lot of the stuff, or even the paper before Twist as well. Like for a lot of these, like a lot of the stuff that gets like hype, that this stuff to work really well is just engineering, right? Like a lot of the teleop stuff, it's getting drilling latency down, right? Like things like that. And I don't know. Engineering unlocks new research too, right? I would say. Yeah. So, but like as long as it's reusable engineering, I guess, right? What do you think? Yeah.
Okay. Cool. Anyway.
All right.
Okay. Cool. I guess.
Paper.
Yeah. That's a wrap. Until we do the next one.
See you next time.
See you next week. Okay.